We are now ready to learn about window function, a very powerful tool in SQL. Now, window functions allow us to do computations and aggregations on multiple rows. In that sense, they are similar to what we have seen with aggregations and group by. The fundamental difference between grouping and window function is that grouping is fundamentally altering the structure of the table, right? Because if I go here and I take this items table and I group by item type, right now I'm looking at about 20 rows, right? But if I were to group, the resulting table would have 3 rows only, because there are only 3 types of items. So that would significantly compress the structure of my table. And in fact, we have seen with the basic law of grouping that after you apply a group by, you have to work around this fundamental alteration in the structure of a table, right? Because here you can see that the items table has 20 rows. But how many rows do you expect it to have after you group by item type? I would expect it to have 3 rows because there's only 3 types of items. And so my table is being compressed, my table is changing its structure, and the basic law of grouping teaches you how to work with that. It tells you that if you want to group by item type, you can't just select power as is, because your table will have 3 rows, but you have 20 values of power. So you have to instead select an aggregation on power so that you can compress those values to a single value for each item type. And if you want to select name, you also cannot select name as is. You also have to apply some sort of aggregation. For example, you could put the names into a list, an array, or so on. But window functions are different. Window functions allow us to do aggregations, allow us to work on multiple values, without, however, altering the structure of the table, without changing the number of rows of the table. So let us see how this works in practice. Now, imagine that I wanted to get the sum of all the power values for my items. So what is the total power for all of my items? So you should already be aware of how to do this in SQL to just get that sum, right? I can do this by getting my fantasy items table and then selecting the sum over the power. So if I take this query and paste it in BigQuery, I will get exactly that. And this now is a typical aggregation, right? The sum aggregation has taken 20 different values of power and it has compressed them down to one value. And it has done the same to my table. It's taken 20 different rows to my table and it has squished them, it has compressed them down to one row. And this is how aggregations work, as we've seen in the course. But what if I wanted to show the total power without altering the structure of the table? What if I wanted to show the total power on every row? In other words, I can take the sum of all the values of power, and this is the same number that we've seen in BigQuery, and I can paste it over here, and hopefully I can now expand it. And this is exactly what I meant. What if I can take that number and put it on every row? And why would I want to do this? Well, there's several things that I can do with this setup, right? For example, I could go here for Phoenix Feather, which is power 100, and I could say, take this 100 and divide it by the total power in this row, and then turn this into a percentage. And now I have this 6.5 approximately percentage. And thanks to this, I can say, hey, look, the Phoenix Feather covers about 6 or 7% of all the power that is in my items, of all the power that is in my game. And that might be a useful information. A more mundane concern could be that this is your budget, so this is the stuff that you're spending on, and instead of power you have the price of everything, and then you get the total sum, right, which is maybe what you spent in a month, and then you want to know, going at the movies, what percent of your budget it covered, and so on. Now I will delete this value because we're not going to use it, and let us see what we need to write to obtain this result in SQL. So once again, we go to the fantasy items table, and I'm gonna move it a bit down, and then we select the sum power, just like before, except that now I'm going to add this over, open round bracket, and close round bracket. And this is enough to obtain this result. Well, to be precise, when I write this in BigQuery, I will want to see a few columns as well. So I will want to see the name, item type, and power. And here I will need a comma at the end, as well as the sum power over. And I will also want to give a label to this, just like I have in the spreadsheet. Now this is the query that will reproduce what you see here in the spreadsheet. So how this works is that the over keyword is signaling to SQL that you want to use a window function. And this means that you will get an aggregation, you will do a calculation, but you're not going to alter the structure of the table. You are simply going to take the value and put it in each row. This is what the over keyword signals to SQL. Now, because this is a window function, we also need to define a window. What exactly is a window? A window is the part of the table that each row is able to see. Now, we will understand what this means much more in detail by the end of this lecture, so don't worry about it. But for now, I want to show you that this is the place where we usually specify the window inside these brackets after the over, but we have nothing here. And what this means is that our window for each row is the entire table. So that's pretty simple, right? Each row sees the entire table. So to understand how the window function is working, we always have to think row by row, because the results can always be different on different rows. So let us go row by row and figure out how this window function is working. So now we have the first row, and what is the window in this case? Meaning, what part of the table does this row see? Well, the answer is that this row sees all of the table. Given that it sees all of the table, it has to do the sum of power. And so it will take this thing, compute a sum over it, put it in the cell. Now that was the first row. Moving on to the second row. Now, what's the window here? What part of the table does this row see? Once again, it sees all of the table. Given that it sees all of the table, it takes power, computes sum over it, gets the result, and puts it in the cell. Now, I hope you can see that the result has to be identical in every cell, in every row, in other words, because every row sees the same thing, and every row computes the same thing, and this is why every row in here gets the same value. And this is probably the simplest possible use of a window function. So let us now take this code and bring it to BigQuery and make sure that it runs as intended. And like I said in the lecture on grouping, you will see that power is blue because BigQuery is getting confused with its functions. So always best practice to put it into backticks to be very explicit that you are referring to a column, but basically what you see here is exactly what we have in our sheet. And now, of course, we have this new field which shows me the total of power on every row, and like I said, we can use this for several purposes. For example, I can decide to show for each item what percentage of total power it covers, right? That's what I did before in the sheet. So to do this, I can take the power and I can divide by this window expression, which will give me the total power. Not sure what happened there, but let me copy paste here. And I can call this percent total power. Now this is actually just a division, so if I want to see the percentage, I will have to also multiply by 100, but we know how to do this. And once I look at this, we can see that when we have power 100, we have almost 6.5% of the total power. So this is the same thing that we did before. And this goes to show that you can use these fields for your calculations. And like I said, if this was your budget, you could use this to calculate what percentage of your total budget is covered by each item. It's a pretty handy thing to know. Now, why do I have to take this to repeat all of this logic over here? Why can't I just say, give me power divided by some power? Well, as you know from other parts of the course, the select part is not aware of these aliases, it's not aware of these labels that we are providing. So when I try to do this, it won't recognize the label. So unfortunately, if I want to show both, I have to repeat the logic. And of course, I'm not limited to just taking the sum, right? What I have here is an aggregation function, just like the ones we've seen with simple aggregations and grouping and aggregations. So instead of sum, I could use something like average, using the backticks, over, right? I need to remember to add the over, otherwise it won't work because it won't know it's a window function. And I can give it a label. And now for each row, I will see the same value, which is the average of power over the whole dataset. And you can basically use any aggregation function that you need. It will work all the same. Few more backticks to put in here just to be precise. But the result is what we expect. Now let us proceed with our explorations. So I would like now to see the total power for each row, but now I'm not interested in the total power of the dataset. I'm interested in the total power by item type. Okay, so if my item is an armor, I want to see the total power of all armors. If my item is a potion, I want to see the total power of all potions, and so on. Because I want to compare items within their category, I don't want to compare every item with every item. So how can I achieve this in the spreadsheet? Well, let us start with the first row. So I need to check what item type I have. And conveniently, I've sorted this so we can be quicker. Now we have an armor. So I want to see the total power for armor. So what I can do is to get the sum function and be careful to select only rows where the item type is armor. And this is what I get. And then the next step would be to simply copy this value and then fill in all of the rows which are armor, because for all of the rows, but again, you have to be careful because the spreadsheet wants to complete the pattern, but what I want is the exact same number. And then all of the rows that have item type armor will have this value because I'm looking within the item type. Now I will do it for potion. So here I need to get the sum of power for all items that are potions. 239, and then make sure to copy the exact same value and to extend it to all potions. And next we have weapons, so sum of all power by weapon, which is here, then copy it and copy it, and then let's see if it tries to complete the pattern. It does, so I'm just going to go ahead and paste it, and now make this a bit nicer, and now I have what I wanted to get. Each row is showing the total power within the items that are the same as the one that we see in the row. Now, how can I write this in SQL? So let me go ahead and write it here. Now, two parts of this query will be the same because we want to get the items table and see these columns, but we need to change how we write the window function. So once again, I want to get the sum of power, and I will need now to define a specific window. Now remember, the window defines what each row sees. So what do I want each row to see when it takes the sum of power? For example, what do I want the first row to see when it takes the sum of power? I want it to see only rows which have the item type armor. Or in other words, all the rows with the same item type. And I can achieve this in the window function by writing partition by item type, by adding a partition. Defining the window as a partition by item type means that each row will look at its item type and then will partition the table so that it only sees rows which have the same item type. So this row over here will see only these 4 rows, and then you will take the sum of power and then you will put it in the cell. And for this, the second, third, and fourth row, the result will be the same because they will each see this part of the table. When we come to potion, so this row over here will say, hey, what is my item type? It's potion. Okay, then now I will only look at rows that have item type potion, and so this will be the window for these 4 rows. And then in those rows, I'm going to take power and I'm going to sum it. And finally, when we come to these rows over here, so starting with this row, it will look at its item type and say, okay, I have item type weapon. Let me look at all the rows that share the same item type. And so its window will look like this. So let me color it properly. Its window will look like this, and then it will take the sum of these values of power that fit in the window and put it in the cell. Second cell sees the same window, sums over these values of power, puts it in the cell. And this is how we get the required result. This is how we use partitioning in window functions. So let's go now to BigQuery and make sure that this actually works. And when I run this, I didn't put a label, but you can see that I'm basically getting the same result. When I have a weapon, I see a certain value. When I have a potion, I see another one. And when I have an armor, I see the third value. So now for each item, I am seeing the total power, not over the whole table, but within the item type. Now, next task, find the cumulative sum of power, which is this column over here. What is a cumulative sum? It's the sum of the powers of this item plus all of the items that are less powerful. So to do this in the spreadsheet, I will first want to reorder my data because I want to see it simply in order of power. So I will actually take this whole range and I will go to data, sort range, advanced options, and I will say that the data has a header row so that I can see the names of the columns. And then I will order by power, ascending. So as you can see, my records have now been sorted in direction of ascending power. Now, how do I compute the cumulative sum of power? In the first row, all we have is 30, so the sum will be 30. In the second row, I have 40 in this row plus 30 before, so I will have 70. When it comes here, I have 50 in this row, and then the sum up to now was actually 70, which I can see by looking at these two cells, or I can see more simply by looking at the last cell. So 50 plus 70 will be 120. And proceeding like this, I could compute the cumulative power over the whole column. Now, for your reference, I have figured out the correct Google Sheets formula that will allow you to compute the cumulative sum of power for our example. And I went ahead and computed it so that we have it for all our data. Now, this is the formula right here, and I'm not going to go in depth into it because this is not a course on spreadsheets, but I will show you the formula just in case you're curious. So the SUMIF function will take the sum over a range but it will only consider values that satisfy a certain logical condition. So the first argument is the range that we want to sum over, and this is the power. And the criterion, so what needs to be true for a value to be considered, is that this value is lesser than or equal to the level of power in this row. So what this formula is saying is take the level of power in this row and then take all the values of power which are lesser or equal and then sum them up. This is exactly what our window function does. And so our formula reproduces this. Now, if you go and look what's the way to do a cumulative sum in Google Sheets, or what's the way to do a running total, there are other solutions, but they do come with some pitfalls. They do come with some corner cases. So this is a formula that's actually reproducing the behavior of SQL. Now let us go back to actually SQL and see how we would write this. So I'm going to take the fantasy items table and I'm still going to select the columns. And now I have to write my window function. Now the aggregation is just the same. So take the sum of power. And now I have to define my window. Now my window is not defined now by a partition, but it is defined by an ordering. Order by power. And when I say order by power in a window function, what's implicit in this is the keyword ask for ascending. So this means that the window will order power from the smallest to the biggest. And I can choose to write this keyword or not, because just like in order by in SQL, when you don't specify it, the default value is ascending from smallest to biggest. So how does this window work? Let's start with the first row, and let's say we need to fill in this value. So I'm going to look at my power level. It is 30. And then the window says that I can only see rows where the power level is equal or smaller. And what are the rows where the power level is equal or smaller to 30? They're these rows over here. So effectively, this is the only part of the table that this window sees on the first row. And then take the sum over power. So sum over 30 is 30. Move on to the second row. The power level is 40. The window says I only see rows where the power level is smaller or equal. And this includes these two rows over here. Now take the sum of power over here, you get 70, put it in the cell. Third row, I have power level 50. I'm only seeing these rows. So take the sum of power over this, it's 120, put it in the cell. And I can continue like this until I get to the highest value in my data set. It's 100. Never mind that it's not the last row, because both of the last two rows, they have the highest value. And when you look at this, when you come to this row and you look at 100 and you say, what's the window? What rows can I see? I can see all rows where power is 100 or less. And that basically includes all of the table, right? It includes all of the table. So when you take the sum of power, you will get the total sum. And in fact, you can see that in this case, the cumulative power is equal to the total power that we computed before, just as we would expect. So this is easy to see here because we have ordered our data conveniently, but it works in any case. And so what the order by does in a window function is that it makes sure that each row only sees rows which come before it, given your ordering. So if I want to order from the smallest power to the biggest power, each row will only see rows that come before it in this ordering, so they have the same level of power or lower, but they don't have a higher level of power. So let us now take it to BigQuery and make sure it works as intended. And I will add an ordering by power. And here I will see the same thing that I've shown you in the spreadsheet. I notice now that some numbers are different, that these two items have 90 instead of 100, but never mind that, the logic is the same and the numbers make sense. Now I'm also able to change the direction of the ordering, right? So let's say that I take this field and copy it just the same, except that instead of ordering by power ascending, I order by power descending. So what do you expect to see in this case? Let's take a look. Now what I see here is that each item is going to look at its level of power, and then it's only going to consider items that are just as powerful or more powerful, right? So it's the exact same logic, but it's reversed. So when you look at the weakest item, potion, it has 30, and so it is looking at all the items because there's no weaker item. And so it finds the total level of power in our dataset. But if you go to the strongest item, like Excalibur, it has a power level of 100. And there's only two items in the whole dataset that have this power level, itself and the Phoenix Feather. So if you sum the power over these, you get 200. So you can see it's the exact same logic, but now each row only sees items that have the same level of power or higher. So when you order inside a window function, you can decide the direction of this ordering by using descending or ascending. Or if you are a lazy programmer, you can omit the ascending keyword and it will work just the same because that's the default. And finally, we want to compute the cumulative sum of power by type. And you might notice that it is in a way the combination of these two requirements. So let us see how to do that. Now, the first thing I want to do is to sort our data in order to help us. So I'm going to get this whole thing and I'm going to say sort range. I'm going to need the advanced options. I have a heading row. And so first of all, I want to order by type. And then within each type, I want to order by power. And this is our data now. Now, for each item, I want to show the cumulative sum of power, just like I did here, except that now I only want to do it within the same item type. So if we look at armor, it's already sorted, right? So I have power 40 and this is the smallest one, so I will just put 40 over here. Next I have this item with power 70, it's still armor, has power 70, and so I'm going to look at these two values and sum them up. Now I have 78, so I will take this plus 78, which is the sum of these three values. And finally, I have 90, which is the sum of those values. And now I'm done with armor, right? I'm beginning with a new item type. So I have to start all over again. I'm looking at potions now. So we start with 30, that is the smallest value. Then we move to 50. So this is now seeing 30 and 50, which is 80. Add 60 to 80, that is 140. And finally, we want to add 99 plus 140, which is another way of saying that we want to add these values, all the values for potion. So this is what we want, cumulative sum of power within item type. So we do it within the item type, and then when we find a new type, we start over. So to calculate it for weapon, I could copy my function from here, paste it in weapon, and then I would need to modify it, right? I would need the range to only include weapon. So that's from C10. So go here, C10 is the first one. And the value that I want to look at here would have to be C10 as well, because I want to start by looking at the power level for the first weapon. And for some reason it's purple. However, it should be correct. It should always be the sum of the previous value. So we start with 65, then we have 65 plus 75, 66, 75, 65, and so on. So this is our result. It's cumulative power within the item type. And to write this in SQL, I will take my previous query over here. And now when we define the window, we can simply combine what we've done before. We can combine the partition by with the order by. And you need to write them in the following order. First the partition and then the order. So I will partition by item type, and I will order by power, ascending. And this will achieve the required result. So for each row in this field, the window will be defined as follows. First, partition by item type, right? So first of all, you can only see rows which have the same item type as you have. But then within this partition, you have to keep only rows where the power is equal or smaller than what you have. So in the case of the first item, you only get this row. Likewise, in the case of the first potion item, you only get this row. If you look at the second armor item, again, it partitions, right? So it looks at all the items which have armor, but then it has to discard those that have a bigger power than itself. So it will be looking at these two rows. And if, for example, we look at the last row over here, so this row will say, oh, okay, I'm a weapon, so I can only see those that are weapon. And then I can only see those that have a level of power that's equal or smaller than mine. And that checks out. Those are all the rows. And in fact, the sum over here is equal to the sum of power by type, which is what we would expect. So once again, let us verify that this works in BigQuery. and I will actually want to order by item type and power, just so I have the same ordering as in my sheet. And I should be able to see that within armor, you have this like growing cumulative sum. And then once the item changes, it starts all over, right? It starts again at the first value, it grows, it accumulates, and then we're done with potions. And then we have weapons, and then again it starts, and then it grows, and it goes all the way to include the total sum of all powers in the weapon item type. So here's a summary of all the variants of windows that we've seen. We have seen 4 variants. Now, in all of those, for clarity, we've kept the aggregation identical, right? We're doing sum over the power field. But of course, you know that you can use any aggregate function here on any column which is compatible with that aggregate function. And then we have defined 4 different windows. The first one is the simplest one. There's actually nothing in the definition. We just say over. And this means that it will just look at all the table. So every row will see the whole table, and so every row will show you the total of power for the whole table. Simple as that. The second window is introducing a partition by item type. And what this means in practice is that each row will look at its own item type and then only consider rows which share the same exact item type. And so within those rows, it will calculate the sum of power. Third window, we have an ordering field. So what this means is that each row is going to look at its level of power because we are ordering by power. And then it's going to only see rows where the power level is equal or smaller. And the reason why we're looking in this direction is that when we order by power is implicitly understood that we want to order by power ascending. If instead we ordered by power descending, it would be the same, just in the opposite direction. Each row would look at its level of power and then only consider rows where power is equal or bigger. And then finally, we have a combination of these two, right? We have a window where we use both a partition and an order. And so what this means is that each row is going to look at its item type and discard all of the rows which don't have the same item type. But then within the rows that remain, it's going to apply that ordering. It's going to only consider rows which have the same level of power or lesser. So it's simply a combination of these two conditions. And this is the gist of how window functions work. First thing to remember, window functions provide aggregation, but they don't change the structure of the table. They just insert a specific value at each row, but after applying a window function, the number of rows in your table is the same. Second thing to remember is that in the window definition, you get to define what each row is able to see when computing the aggregation. So when you are thinking about window function, you should be asking yourself, what part of the table does each row see? What's the perspective that each row has? And there are 2 dimensions on which you can work in order to define these windows. One is the partition dimension and the other is the ordering dimension. The partition dimension cuts up the table based on the value of a column. So you will only keep rows that have the same value. The order dimension cuts up the table based on the ordering of a field. And then depending on ascending or descending, depending on the direction that you choose, you can you can look at rows that are after you in the ordering, or you can look at rows that are before you in the ordering. And you can pick either of these, right? Either partitioning or ordering, or you can combine them. And by using this, you can define all of the windows that you might need to get your data. Now, as a quick extension of this, I want to show you that you're not limited to defining windows on single fields, on single columns. You can list as many columns as you want. So in this example, I'm going to the fantasy characters table. I'm getting a few columns, and then I'm defining an aggregation on a window function. So I'm taking the level field and I'm summing it up, and then I'm partitioning by two fields actually, by guild and is alive. So what do you expect to happen if I do this? This is actually the exact same logic as grouping by multiple fields, which we've seen in the group by. Now the data is not going to be divided by guild and is not going to be divided by whether the character is alive or not, but by all the mutual combinations between these fields. Okay, so Mirkwood and true is one combination, and so the people in here are going to fit together, right? So in fact, we have two characters here, 22 and 26, and their sum is 48. So you can see here that they both get 48 for sum of level. And likewise, when you look at Shirefolk true, these three, they all end up in the same group. And so they all share the same sum of level, which is 35. But Shirefolk false, this is another group, and they're actually alone, right? It's 12, and then the sum is 12. So again, when you partition by multiple fields, the data is divided in groups that are obtained by all the combinations between the values that these fields can have. And if you experiment a bit by yourself, you should have an easier time to convince yourself of this. Likewise, the same idea applies to the order part of a window. We have until now, for simplicity, ordered by one field. To be honest, most times you will only need to order by one field, but sometimes you might want to order by different fields. So in this example, you can see that we are defining our ordering based on two fields, power and then weight. And then based on that ordering, we calculate the sum of power, and this is again a case of cumulative sum. However, now the ordering is different, and you will realize this if we go to the most powerful items in our data, these last two, which are both at 100. So if you remember, when we were ordering by power alone, these two fields had the same value in this window function, because when you order just by power, they are actually the same. They both have 100. But because now we're ordering by weight, and again, we're ordering by weight ascending, so from the smallest weight to the biggest weight, now the phoenix feather comes first, because although it has the same power as Excalibur, the phoenix feather is lighter. And because it comes first, it has a different value for this aggregation. And of course, we have the power to say ascending or descending on each of the fields by which we order. So if I wanted to reverse this, I could simply write descending after the weight, and be careful that in this case, descending is only referring to weight, it's not referring to power. So this is just as if I've wrote this, right? So this one can be omitted because it's ascending by default, but I would write both to be clear. And now if I run this, you will see that our result is reversed, right? Excalibur comes first because we have weight descending, so it's heavier. And then last we have the phoenix feather, which is lighter. And again, understanding this theoretically is one thing, but I do encourage you to experiment with this, with your data, with exercises, and then you will be able to internalize it. And now we are back to our schema for the logical order of SQL operations, and it is finally complete again because we've seen all of the components that we can use to assemble our SQL query. And now the question is, where do window functions fit into this? Well, as you can see, we have placed them right here. So what happens is that, again, you get your data, and then the where filter runs, dropping rows which you don't need. And then you have a choice whether to do a group by, right? Now, if you do a group by, you're going to change the structure of your table. It's not going to have the same number of rows. It's going to have a number of rows that depends of the unique values of your grouping field or the unique combinations of values of your fields if you have used more than one. If you group, you will probably want to compute some aggregations, and then you may want to filter on those aggregations, meaning dropping rows based on the values of those aggregations. And here is where window functions come into play. It is on this result that window functions work. So if you haven't done a group by, then window functions will work on your data after the where filter runs. If you have done a group by, window functions will work on the result of your aggregation. And then after applying the window function, you can select which columns you want to show, give them labels, and then all the other parts run, right? So you can choose to drop duplicates from your result, meaning duplicate rows which have the same value on every column. You can stack together different tables, right? You can put them on top of each other. And then finally, when you have your result, you can apply some ordering, and also you can cut the result. You can limit it so you only show a few rows. And this is where window functions fit into the big scheme of things. And there are some other implications of this ordering. One interesting one is that if you have computed aggregations, such as the sum of a value within a class, you can actually use those aggregations in the window function. So you can sort of do an aggregation of an aggregation. But this is, in my opinion, an advanced topic, and it doesn't fit into this fundamentals course. It may fit someday in a later, more advanced course. I want to show you another type of window functions which are very commonly used and very useful in SQL challenges and SQL interviews. And these are numbering functions. Numbering functions are functions that we use in order to number the rows in our data according to our needs. And there are several numbering functions, but the three most important ones are, without any doubt, row number, dense rank, and rank. So let's see how they work in practice. Now what I have here is a part of my inventory table. I'm basically showing you the item ID and the value of each number. And conveniently, I have ordered our rows by value ascending, okay? And now we're going to number our rows according to the value by using these window functions. Now, I've already written the SQL query that I want to reproduce. So I'm going to the fantasy inventory table, and then I'm selecting the item ID and the item value, as you see here. And then I'm using three window functions. So the syntax is the same as what we've seen in the previous exercise, except that now I'm not using an aggregation function over a field like I did before when I was doing sum of power and so on, but I'm using another type of function. This is a numbering function, okay? So these functions over here, they don't actually take a parameter. As you can see that there's nothing between these round brackets because I don't need to provide it an argument or a parameter. All I need to do is to call the function. But what's really important here is to define the correct window. And as you can see, in the three examples here, the windows are all the same. I am simply ordering my rows by value ascending, which means that when it's going to compute the window function, every row will look at its own value and then say, okay, I'm only going to see rows where the value is the same or smaller. I'm not going to be able to visualize rows where the value is bigger than mine. And this is what the window does. So the first row over here will only see value of 30. The second row will see these. The third row will see these, and so on up until the last row, which will see itself and all the other rows as well. Now let us start with row number. So row number is going to use this ordering over here in order to number my rows. And it's as simple as saying, putting 1 in the first row, 2 in the second one, 3, 4, and so on. So if I extend this pattern, I'm going to get a number for every row. And that's it. That's all that row number does. It assigns a unique integer number to every row based on the ordering that's defined by the window function. And you might think, oh, big deal. Why do I need this? Don't I already have like row numbers over here in the spreadsheet? Well, in SQL problems, you often need to order things based on different values, and row number allows you to do this. You can also have many different orderings coexisting in the same table based on different conditions, and that can come in handy, as you will discover if you do SQL problems. Now let's move on to ranking. So first of all, we have dense rank. Okay, and ranking is another way of counting, but is slightly different. Sometimes you just want to count things, sometimes like we did here in row number, like, I don't know, you are a dog sitter and you're given 20 dogs and you getting confused between all their names, and then you assign a unique number to every dog so that you can identify them. And you can sort them by, I don't know, by age or by how much you're getting paid to dog sit them. Sometimes, on the other hand, you want to rank things, like when choosing which product to buy or expressing the results of a race, right? And the difference between ranking and counting can be seen when you have the same value, right? So when you want to simply number, like we did here, when you want to simply assign a different number to each element, and two things have the same value, then you don't really care, right? You need to sort of arbitrarily decide that, okay, one of them will be number 2 and one of them will be number 3. But you cannot do the same for ranking. If two students in a classroom get the best score, you can't just randomly choose that one of them is number 1 and the other is number 2. They have to both be number 1, right? And if two people finish a race at the same time and it's the best time, you can't say that one won the race and the other didn't, that because one is number 1, the other is arbitrarily number 2. They both have to be number 1, right? They have to share that rank. And this is where ranking differs. So let's go in here and apply our rank. Now we are ordering by value ascending, which means that the smallest value will have rank number 1. And so 30 has rank number 1. Now we go to the second row. And again, remember, window functions, that you always have to think row by row. You have to think what each row sees and what each row decides. So again, the row is going to order by value. So it's only going to see these values over here, and it has to decide its rank. So this row says, oh, I'm not actually number 1 because there is a value which is smaller than me. So that means I have to be number 2. And then we get to the third row. And this row is seeing all the values that come before it, right? They're equal or smaller. And now it's saying, oh, I'm not number 1 because there's something smaller, but then the value 50, which this guy has, is rank 2, and I have the same value, number 50. We arrived in the same spot, so I must have the same rank. Okay, and this is the difference between row number and rank, that identical values get the same rank, but they don't get the same row number. And now we come to this row, which is 60, so it's going to look back and it's going to say, oh, from what I see, 30 is the smallest one, so it has a rank of 1, and then you have 50 and 50, they both share a rank of 2, but I am bigger, so I need a new rank. And so what am I gonna pick now as a new rank? Well, I'm going to pick 3 because it's the next number in the sequence. Then the next one is going to pick 4, the next one is going to pick 5, and then we have 6, and then it proceeds in the following way. So I'll do it quickly now. So 7, 8, 9, 10, 11, and again, careful here, we're sharing the same value, so they are both 11. Next we can proceed to 12, 13, again the same value, right? So they have to share the 13th spot. 14, so 14 for 1700, and then 14 again, and then 15, and then 16. And this is what we expect to see when we compute the dense rank. And finally, we come to rank. Now, rank is very similar to dense rank, but there is one important difference. So let's do this again. Smallest value has rank number 1, like before. And then we have 50, which has rank number 2. And then 50 is once more sharing rank number 2. And now we move from 50 to 60, so we need a new rank. But instead of 3, we put 4 over here. Why do we put 4? Because the previous rank covered 2 rows, and it sort of ate the 3. It sort of expanded to ate the 3. So based on the rules of simply rank, we have to lose the 3 and put 4 over here. So this is just another way of managing ranking, and you will notice that it conveys another piece of information compared to dense rank, because not only I see that this row over here has a different rank than the previous row, but I can also see how many members were covered by the previous ranks. I can see that in the previous ranks, they must have involved 3 members because I'm at 4 already. And this piece of information was not available for dense rank. So I will continue over here, and so I have a new value, which is rank 5, and then I have rank 6, rank 7, rank 8, rank 9, rank 10, rank 11. Now I have rank 12, and again I have to share the rank 12 because 2 identical values. But now, because 12 has eaten up 2 spots, I can't use the 13 anymore. The second 12 has like eaten the 13, and so I need to jump straight to 14. 15, 15 again, and now I have to jump to 17 because 15 had 2 spots. 17 again, and now I have to jump to 19, and then finally I have 20. So you can see that the final number is 20 for rank, just as with row number, because it's not only differentiating between ranks, but it's also counting for me how many elements have come before me, how many rows are contained in the previous ranks. I can tell that there's 19 rows in the previous ranks because of how rank works. Whereas with dense rank, we ended up using only 16, ended up being only up to 16. So we sort of lost information on how many records we have. And this might be one of the reasons why by default you have this method of ranking instead of this method of ranking. Even though dense rank seems more intuitive, when you are building the ranking yourself. So we can now take this query, and hopefully I've written it correctly, and go to BigQuery and try to run it. And as you can see, we have our items. They are sorted by value. And then we have our numbering functions. So row number should go from 1 to 20 without any surprises, because it's just numbering the rows. Dense rank should have rank 1 for the first, and then these two should share the same rank because they both have 50, and then the next rank is 3. So just as I've shown you in the spreadsheet. Similarly here, you have 11, 11, and then 12. Rank instead starts off just the same. Smallest value has rank number 1, and the next two values have rank number 2. But then after using up 2 and 2, it's like you've used up the 3, so you jump straight to 4. And after doing 15 and 15, you jump straight to 17. After doing 17, 17, you jump straight to 19. And then the highest number here is 20, which tells you how many rows you're dealing with. Of course, what you see here are window functions. They work just the same as I've shown you. And so you could pick up rank and you could order by value descending, and then you will find the inverse of that rank, in the sense that the highest value item will give you rank 1, and you will go from there. And the lowest value item will have sort of the biggest rank number. And rank is often used like this, you know, the thing that has the most of what we want, you know, the biggest salary, the biggest value, the most successful product. We rank it, we make it so that it's rank 1. It's like the first in our race. And then everyone else goes from there. And so we often have we order by something descending when we calculate the rank. And of course, because these numbering functions are window functions, they can also be combined with partition by if you want to cut the data into subgroups. So here's an example on the fantasy characters table. We are basically partitioning by class, meaning that each row only sees the other rows that share the same class. So archers only care about archers, warriors only care about warriors, and so forth. And then within the class, we are ordering by level descending. Okay, so the highest levels come first, and using these to rank the characters. Okay, so if I go here, then I can see that within the archers, the highest level archer has level 26, so they get the first rank. And then all the others go down from there. And then we have our warriors. And the highest level warrior is 25, and they also get rank 1 because they are being ranked within warriors. So this is like when you have races and there are categories. This is like when you have a race and there are categories within the race. So there are like many people who arrive first because they arrive first in their category. It's not that everyone competes with everyone. And so on and so forth. You can see that each class of character has their own dedicated ranking. And you can check the BigQuery page on numbering function if you want to learn more about these functions. You can see here the ones we've talked about: rank, row number, and dense rank. There are a few more, but these are the ones that are most commonly used in SQL problems. And because I know that it can be a bit confusing to distinguish between row number, dense rank, and rank, here's a visualization that you might find useful. So let's say that we have a list of values, which are these ones, and we are ordering them in descending order. So you can see that there's quite some repetition in these values. And given this list of values, how would these different numbering functions work on them? Right, so here's row number. Row number is easy. It just assigns a unique number to each of them. So it doesn't matter that the values are sometimes the same. You sort of arbitrarily pick one to be 1, the other to be 2, and then you have 3. And then here you have 10, 10, 10, but it doesn't matter. You just want to order them. So you do 4, 5, 6, and then finally 7. Dense rank is actually cares about the values being the same. So 50 and 50, they both get 1. 40 gets 2. And then the 10s get 3, and then 5 gets 4. So easy, the rank just grows using all the integer numbers. Dense rank is also assigning rank 1 to 50 and 50, but it's also throwing away the 2 because there are 2 elements in here. Then the next one is getting rank 3 because the 2 has already been used. And then the next batch, 10, 10, 10, is getting rank 4, but it's also burning 5 and 6. And the next one then can only get rank 7. So these are the differences between row number, dense rank, and rank visualized.